Hi everyone, this is the video overview for Lab 8 on tectonic hazards. Now, what do I mean by hazards? Well, hazard is, in this case is just referring to a situation or event that could be potentially dangerous arising from the plate tectonics of the Earth. This is not the same as risk associated with these situations or events, which is more of a societal construction, such as if there's lots of people living in close proximity to a volcano, there would be very high risk associated with the hazard, which could occur whether there's risk or not. So it's important to keep this in context with the tectonic plate theory that we learned about in last lab. Remember that these tectonic plates may appear to move very, very slowly, and they do, especially over the course of a human lifetime. But uh, through science, we've discovered that these tectonic plates have actually been all over the Earth at various points in time. To illustrate this, I'd like to show you a video from the University of Sydney, basically showing the last million years of tectonic plate activity and how these plates have shifted around. So the timer at the top is ticking down. That MA refers to million years ago. Now the continents start to split apart to resemble the shapes that we are familiar with today. So with keeping this in mind, that tectonic plates move very slowly, but there's so much force involved. You know, how much energy it would take to move these giant sheets of rock floating on top of a molten layer. I mean, that's mind-blowing. So, of course, it would make sense that these hazards, which such as volcanoes, earthquakes, and tsunamis, which themselves release so much energy, arise most commonly from tectonic plate activity. So, the most straightforward one to understand how this relates to tectonic plates would be earthquakes. Earthquakes are measured with a seismograph. Often you may be familiar with the Richter scale, which is just a logarithmic scale, basically how much magnitude there is of shaking. It goes up to 10. We've never had a magnitude 10. It would just be crazy. But even like magnitude 7s, 8s especially are really bad earthquakes. Most commonly, earthquakes are around the 2 to 4 range. And there is this theory that explains how and why earthquakes occur. That's not completely proven yet, that you can look into on your own, called the elastic strain cycle. It's pretty interesting, but I'm not going to go too deep into that. Earthquakes, the highest intensity ones, like those magnitude 7s, 8s, those really bad ones, are most they're related to subduction zones, which we've already learned is when one tectonic plate, usually the oceanic crust, goes underneath the continental crust, and that is called subduction. When one plate goes underneath another, and that continent or that oceanic crust gets recycled. It goes down into the earth, it melts, it gets recycled, and that continental crust may be pushed up. Magma may be forced upward. There could be shifting to release, sudden bursts of energy, which is basically an earthquake. So these greatest intensity earthquakes all seem to occur along the Pacific Ocean on what we call the Ring of Fire. I'm going to talk about that in a minute. Now, closer to home, you may be surprised to find that there is a fault zone with earthquakes that may happen every day in the states such as Missouri, Arkansas, Illinois. These are very low intensity earthquakes. They're usually less than 5 or 6 on the Richter scale. So these are very minor, don't cause damage, much if any. And this is caused, now obviously the Missouri, Arkansas, Illinois is not on the edge of a plate boundary. It's actually in the middle of the North American plate. So what causes this? This is actually caused by localized compression, just from regional forces squishing this particular area, all converging on this area called the New Madrid fault zone. Now, you don't need to know all those super details, but I want you to understand that, like, close to home, there actually is another place that you can have earthquakes, and it's very common, but it's not near a plate boundary. Now, that is a unique exception. Most of the earthquakes that do occur on the Earth are along plate boundaries. So here actually shows you where all of the global earthquakes would occur over the last 100+ years, and the highest intensity ones are only shown here. Not even the minor ones. That's why you don't see any in this New Madrid fault zone, because they're below the 7 Richter scale cutoff here on this map. So that's why you don't see any in Missouri. But this illustrates the point that if you look at this faint yellow line showing the plate boundaries, especially along this ring of fire in the Pacific Ocean, that is where most of the highest intensity earthquakes occur. And the Richter scale is logarithmic, which just means that if you go up one number, that is 10 times greater than the number before it. So, a 7 is much worse than a 6, which is still much worse than a 5, 4, etc. So in lab today, you're going to be looking at the distribution of earthquakes. It's a little more recent than this map here, but you can play around with that in Google Earth. You'll have to upload a KML file, again, into Google Earth to see that layer. But that should help you understand that these earthquakes are most commonly associated with these plate boundaries, especially subduction zones. Now, this is going to show you what happens.
We're standing here in the Papatia Fault, a few kilometres south of the Clarence River Bridge on the Kaikoura coast. Looking here at the fault plane, the plane of movement along the fault itself, where this side here has moved up by about 1.5 metres. And we can see the gravels here and the gravels on that side. But what's really interesting is that we can see lines of movement here on this fault plane which are moving down a little bit in this fashion. And that means we can see, it looks impressive that we're standing here 1.5 metres high, but in fact most of the movement has been along a plane something like this. So this side here has moved forwards by many, many metres. These fault scarps form very, very quickly, and we know from earthquake physics that probably this fault scarp ruptured across here at a speed of about 3 kilometres a second. So this has uplifted a very large area of new reef here, and the locals here describe not the earthquake noise, but the noise of water running off the top of this uplifted platform here. They said that the noise was just horrendous. And on this side, on the downthrown side of the fault, it's actually still even come up by about 1.5 metres. On the other side, there's as much as 6 metres of uplift.
Okay, so the point that this video is showing is that 6 meters of uplift can occur in the blink of an eye. 3 kilometers per second, that's how fast this chunk of rock might move. That is so fast. And what that does when that sort of earthquake occurs underwater, you might have tsunamis because it displaces this water. Now, I'm not going to show you this video or the link on the left, but if you're interested, I encourage you to check it out. This TED Talk is actually required by the lab. It's a 3-minute watch. It's pretty light, but tsunamis occur when water is displaced, which is very common with earthquakes, but it can also happen with underwater volcanoes or even an underwater landslide. And sometimes these all might occur together too. So tsunamis are actually very hard to predict. Nowadays, science has gotten better and we start to have an early warning system, but there might not be very much warning at all, other than what you might see along the coast itself when water gets sucked back away to sea. That's usually a telltale sign that the wave is going to come. So that's all I'm going to talk about tsunamis. Now, what is often the most exciting hazard, it makes for great visuals, but it can also be very hazardous, of course. This whole lab is on tectonic hazards. Volcanoes are another huge release of energy from the earth. This is, thermal energy, kinetic energy, chemical energy, and these earthquakes may occur in different types too. Earthquakes or excuse me, volcanoes uh, can be classified into four loose categories based on their shape and size, how they form, and the actual eruption itself could be linked to that type of volcano. So, volcanoes, there's a lot more info in your textbook, um, but I'm not going to go too deep on volcano science in this lab. But volcanoes can release pyroclastic flow, which is probably the most scary one. Temperatures of hundreds and hundreds of degrees Celsius, all throwing pumice and ash down the slope. This is very explosive. This is a video of Mount Etna erupting. This is a very this is showing pyroclastic flow and ash being lifted into the atmosphere, just ejected by the earth. So ash is another one that can be part of an eruption from a volcano. Gas such as CO2 or more noxious gases that can actually just poison or uh, burn your lungs. These are not nice friendly gases. Um, but also the I would say the most the one you might think of first is lava flows as well too. These are often the least hazardous. Actually, the lava flows are not usually the ones that pose the most risk to human life, because lava flows are usually pretty slow. I mean, lava would flow downhill. It's a liquid. It's just a molten rock. There can be different types of lava flows too. You can see so many videos of this online. It's really cool, such as the uh, volcanoes that are currently erupting in Hawaii, Iceland. There's ones all over the earth. At any point in time, there's going to be a volcano erupting. They're not usually very hazardous, though. Though the most hazardous ones are usually the composite volcanoes, which may take hundreds or sometimes thousands of years to erupt again. They're very irregular. And so this is to just step back here and reiterate how and why volcanoes would be most commonly associated with subduction zones, such as along the west coast of the United States, Chile, Alaska, all the way down the other side of the Ring of Fire on the west coast of or the west side of the Pacific Ocean, Japan, Philippines, Indonesia, etc., is that subduction is occurring, and this oceanic crust is getting forced back down into the mantle, at which point temperatures and pressures become very great. They may force some of that newly melted oceanic crust up to the surface because there's all this extra rock being pushed underneath, and it has to go somewhere. So one way that pressure can be released is that it comes back up to the surface, and you end up with volcanoes. Um, this diagram is showing a composite volcano, but that's not the only time, or that's not the only situation that can occur. And there's also another way that volcanoes can commonly form, and that's related to hotspots. A hotspot is basically just think of it as a spot where the crust of the earth might be very thin, or the mantle, for whatever reason, the asthenosphere, might be very close to the surface. Now, when I say surface, this could be underwater, which is very common to get these island chains that form under a hotspot. Because remember, the oceanic crust is usually much thinner than the continental crust, so it's easier for a hotspot to occur in the ocean. So a hotspot often forms a chain of volcanoes, not because the hotspot moves, but because the crust over the top of the hotspot would move. And at different points in time, the hotspot would become more active or less active. These things are very dynamic too. So that's why you don't have just like a steady line of why the Hawaiian Islands are islands rather than just one straight line of one major island. Is because this hotspot becomes active or inactive at different points in time. And these hotspot volcanoes often form shield volcanoes, which um, uh, are very wide, not very steep slope, and they're very common in the ocean. So that's one way you could identify shield volcanoes. Now, to go into greater detail about the types of volcanoes that we have, and the last section of lab is going to ask you to characterize a few volcanoes in Google Earth. To start, let's talk about the cinder cone or scoria cone. This is basically, it's often very relatively small compared to the other types. It has steep sides and it's made up of loose material, gravel, sand, small particles that have accumulated very loosely to form basically a mound, a cone, right? Shield volcanoes, on the other hand, are very wide, like I said. These are built up over vast periods of time with mostly fluid lava flows. So the fluid wants to, spread out, which is, you might think that's how we get the wide, gradual slope of the shield volcano. Composite volcanoes these are the most hazardous. These are the most explosive. These are the quintessential volcanoes you might think about. If you've ever seen videos of the Mount St. Helens eruption, that was a composite volcano. And these form, it's a little more complicated how they form. They're built up of just different strata or layers over time of different types of material. They might have highly variable magma chambers. So these are harder to classify, but you can identify them with their rocky sides. They're very steep slopes. They're usually taller than cinder cones. And this fourth type is a dome, which is not per se a volcano itself. It's usually associated with like another composite volcano or shield volcano. A dome can form basically of highly viscous magma. So very, very sticky, not very liquidy magma that doesn't want to flow away from the eruption site, and it just sort of builds up. Domes can often rise, and that's how volcanologists might track the risk of a volcano actually erupting is by its actual dome, which is another way you might think of is just the magma starting to push out, but not yet ready to flow away. So in lab today, you should think of these types of volcanoes for what we're asking for, and use things like its size, its height relative to its width. Any context clues you might have. Is this on an island in the ocean, etc.? Or its slope. How steep is it? Then you're gonna have to actually measure the heights of some of these volcanoes in lab today. Basically, with Google Earth, you hover over one point and you hover over another point, and Google Earth will tell you its elevation at the 2 points. So to actually do the lab, you should download the 2KML files first and import them into Google Earth. One of them is the same as last lab, the plate boundaries KML file. So if you still have that, you can use it again. But this 2.5 month depth animated link, that's showing earthquakes from the USGS. So it's pretty interesting. It's recent and it's updated periodically. And disregard that due date. So I'm going to end there. And as usual, if you have any questions or if you run into issues, please reach out to me as soon as possible. Email or Teams is good. And I hope you enjoy this lab on hazards, which is exciting, but also a little scary to think about.